In this video, we'll do two more examples of general solutions and phase portraits for constant coefficient systems. So the system here, the matrix is minus 2, 1, minus 12, 5. So our first step is always to find the eigenvalues and eigenvectors. The determinant of A minus lambda I is the determinant of minus 2 minus lambda, 1 minus 12, 5 minus lambda, which is minus 2 minus lambda, 5 minus lambda plus 12. I see a lambda squared, a minus 5 lambda, a plus 2 lambda, a minus 10 plus 12, lambda squared minus 3 lambda plus 2, which factors as lambda minus 1, lambda minus 2. So I have lambda equals 1 and lambda equals 2. And so I know right away this will be a nodal source because I have two positive eigenvalues. Now to draw it, I need the eigenvectors as well. So for lambda equals 1, the matrix becomes minus 3, 1, minus 12, 4. The bottom row is just 4 times the top one, so it'll cancel out. And this will tell me that an eigenvector that I need here is 1 and 3. For lambda equals 2, the matrix becomes minus 4, 1, minus 12, and 3. Again, the bottom row is 3 times the top, so my vector here is going to be 1, 4. Which means that I can write the general solution out just based on this information here. General solution is C1 times 1, 3 e to the t, because lambda is 1 there, and plus C2, 1, 4 e to the 2t. Now what does our phase portrait look like? Well, we have our two straight line solutions along 1, 3, which will be somewhere like that, going away, and 1, 4, which is close but slightly steeper, also going away. Now we know that as t goes to plus infinity, we're going away from the origin because everything's positive here, and the purple term is more important. So if I start a solution somewhere in here, I have to go to plus infinity along the purple line, so I'm going up this way, and come into 0 along the green line. For these problems, those will always be opposite lines. If you ever think you should go both infinity and 0 along the same line, that's probably not right with the logic here. I should approach this way along the green line like this, and I can fill in the gap for the rest of these. For a point over here, you need to go to infinity along the purple line and into 0 along the green line, which involves a giant loop there. But that's just how this is going to work out because of the different ways we have to get into 0, because we can't cross over the purple line to get to the other side. I can fill in the other two as well. And that is the picture that we get for our nodal source here for this problem. It looks a fair bit different from the one we did the previous example. That was 1 minus 1 and 1, 1 for the eigenvectors, but that's just because of the angles between these vectors. You get some different looking pictures depending on how close or far apart the vectors are, and this one looks a little bit strange because of it, but the ideas of how you build it is still the same. For a second example, we have the matrix 5 minus 8, 4 minus 7, and we follow the exact same process here. Find the eigenvalues, also the determinant of this matrix, 5 minus lambda minus 8, 4 minus 7 minus lambda, which is 5 minus lambda minus 7 minus lambda plus 32, lambda squared plus 7 lambda minus 5 lambda minus 35 plus 32, lambda squared plus 2 lambda minus 3, which is lambda plus 3 lambda minus 1. So that I have eigenvalues at lambda equals minus 3 and 1, which means this will be a saddle point because I have eigenvalues of opposite signs. All right, now let's hunt for those eigenvectors. So for lambda equals minus 3, the matrix becomes 8 minus 8, 4 minus 4, because I'm adding 3 on the diagonal. This will have a eigenvector that I want here of 1, 1, because it both are reduced to 1 minus 1 when you row reduce. And for lambda equals 1, matrix becomes 4 minus 8, 4 minus 8, which has an eigenvector of 2, 1. So row reduce to 1 minus 2 when I row reduce. So from that, I write a general solution, which will be C1. Our first eigenvector was 1, 1, e to the minus 3t, plus C2, 2, 1, e to the t. And then we can draw out our phase portrait. For our two eigenvectors or straight line solutions, we have 1, 1, which is going in because the eigenvalue is negative. And we have 2, 1, which will be flatter, because that's 2 in the x direction, 1 in the y direction, and that one's going out. Because I have 1 in, 1 out, I get a saddle, and the picture there looks pretty similar all the time. It's just that wherever I'm at, I need to follow the purple line away, because that's going away. And then when I'm coming in towards this way, I gotta come in along the green line. Follow the arrows both times. And that's the picture you get for this saddle point. Saddle points usually look pretty similar just because you always have 1 in, 1 out, and the solutions always curve sort of from one to the other, no matter how these branches are laid out. So there's a couple examples of finding general solutions and using them to help draw phase portraits for these constant coefficient systems where you have real and distinct eigenvalues.